Okay, hello everybody. My name is Satoshi Hoshino. I'm from Utsunomiya University, Japan. Today I'm going to talk about comparison of end-to-end continuous and discrete motion planners for autonomous mobile robots. All right, first off, for autonomous navigation of mobile robots, as shown in this picture, motion planning in order for the robot to move toward a destination while avoiding obstacles is an essential technique. So in recent years, motion planners based on a deep learning technique have been proposed. Uh, in the motion planners, deep neural networks are used to approximate a relationship between sensor inputs and motor outputs, such as velocity and angular velocity. So this is a so-called end-to-end or just E2E motion planner. The E2E motion planner is roughly divided into continuous and discrete types, depending on the outputs. For a regression problem, the E2E motion planner that determine the continuous values of for example, velocity and angular velocity is used. And for a classification problem, the E2E motion planner that determine the discrete values of the velocity and angular velocity is used. Actually, many of the researchers have focused on the E2E continuous motion planners rather than the discrete motion planners. On the other hand, we have actually so far proposed a discrete motion planner based on the deep neural network. In this motion planner, range data and goal direction were used as the input. As for the range data, we assume that the robot is equipped with a 2D LiDAR sensor, as you can see here. Then each time the robot scans the environment from 1 to blah, 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 in total, n range data are used as the inputs. The range data enables the robot to avoid the obstacle, for example, just around here. However, the robot based on this motion planner move in a different direction from the destination. Therefore, we use the goal direction as an additional input. The robot localizes the position and orientation in a global map of the environment. So in this map, a destination or goal, in this case, is designated by an operator. After that, the path planning from the robot toward the goal or destination, a direction angle here, phi, is used, is derived and used as the goal direction in the input, okay? The inputs are then classified into the control commands such as go straight, turn right, and turn left. For this purpose, the output values of the velocity and angular velocities were discretized. Okay, here let me show you the obstacle avoidance movies of the robot based on the E2E discrete motion planner. First off, as you can see in the left movie, the robot successfully avoided the front obstacles toward the goal destination, okay? In the right movie, we can see that the robot successfully moved toward the destination after the obstacle avoidance because the destination is just over here, around here, okay? Yes. So in this presentation, we further develop an E2E continuous motion planner in addition to the discrete motion planner and compare the navigation performance to each other. Here, the top figure shows a structure of the deep neural network used for the continuous motion planner, and the bottom figure shows the structure of the deep neural network used for the discrete motion planner. For both of the E2E motion planners, the same inputs, which are range data and goal direction, are used. The outputs from the discrete motion planner are discrete values of the velocity and angular velocity, which indicate the control command such as go straight, turn right, and turn left. On the other hand, the outputs from the continuous motion planner are continuous values of the velocity and angular velocity. These deep neural networks used in the two motion planners are enhanced through the supervised learning. For this purpose, we adopt a learning from demonstration approach. For this approach, we have so far developed this kind of a teaching system. As you can see in this picture, first, the operator is now controlling this mobile robot through the joystick by watching the front display. So the motion commands are sent to the robot through the joystick. In this movie, the robot is now moving on the basis of the operation, okay? Since the robot is equipped with a 2D LiDAR sensor, the range data is displayed for the operator. So the operator is now controlling the robot by watching this monitor, okay? The teaching system allows the operator and robot to have the same environmental information. So through the learning from demonstration approach, training data sets are simultaneously acquired. The inputs are the range data and the goal direction. The outputs are the motion commands. For the continuous motion planner, the velocity and the angular velocity are directly recorded. For the discrete motion planner, the velocity and angular velocity are discretized, as you can see here, here, and here. And these are labeled as go straight, turn right, and turn left. And for the network training, these motion commands are used as the supervisory signals. Okay. The network training is executed through the supervised learning. For this purpose, in total, 3,000 training data sets were acquired from the learning from demonstration approach, as you can see in these movies. So the robot is now moving on the basis of the operation. Okay, the operator is now controlling the robot by watching this monitor. And these figures show the result of the network training. As the network training proceeded, the loss values of each deep neural network was decreased. This result indicates that the deep neural networks increased the regulation and the classification performance. Okay. Finally, the loss value at the 30th epoch was minimized, so the deep neural network based on these results are used as the E2E continuous motion planner CMP and the discrete motion planner DMP. For autonomous navigation of the mobile robot, we prepared two environments, as you can see in these pictures, 1 and 2. The robot moves from S here toward G, S here toward G. Okay, so in environment 1, the robot is required to avoid the obstacle. On the other hand, in environment 2, the robot is able to reach the destination without avoiding obstacles. And for the environment without these obstacles, we built a map beforehand using SLAM. The bottom figures show the map where the obstacles such as table and chairs. These movies show the obstacle avoidance behavior of the robot based on the CMP, continuous motion planner, and DMP, discrete motion planner in environment 1. We can see that the robot successfully moved toward the destination while avoiding the obstacles. Okay, here let me show you the trajectories of the robot at the navigation result. The robot based on both the motion planners, CMP and DMP, exhibited almost the same behavior For your information, let me show you the angular velocity sent to the robot based on the motion planners. As you can see, the discrete angular velocity was determined in the right. On the other hand, the continuous angular velocity was determined in the left. So these results indicate that compared to the DMP, the robot based on the CMP achieved more fluid obstacle avoidance. On the other hand, it is also notable that even the robot based on the DMP avoided the obstacles and reached the destination, well, the discretized angular velocity. Therefore, the sufficient obstacle avoidance capability of the two motion planners, regardless of the regression and the classification problems, was shown from these results. Okay, so next, these movies show the robot moving in a straight line toward the destination in environment 2. The robot based on both the CMP and DMP succeeded in moving toward the destination. In this regard, however, the robot based on the CMP in the left movie slightly moved just around here. Please have a look at this movie again, just around here, and so, yeah, this one, okay? On the other hand, in the light, the robot based on the DMP completely moved in a straight line. The robot behavior is due to the angular velocity. From the trajectories, we can see the robot based on the CMP slightly weaved. Therefore, we compare the angular velocity as shown in these figures. As can be seen in the left figure, although the obstacle avoidance was not required in this environment, the angular velocity other than omega is 0 was decided by the CMP. And in contrast to this result, the angular velocity of omega is 0 was constantly decided by the DMP as shown in this light figure. In other words, the result of the discretized angular velocity, the robot based on the DMP moved with no influence of the obstacles. Therefore, while the CMP resulted in the fluid motion for obstacle avoidance, the highest straight line stability of the DMP was shown. Okay, so in order to improve the straight line stability of the CMP, the network training was further executed. And from these figures, even though the deep neural network at the 50th and 100th epoch was used, the angular velocity other than omega is 0 was decided and sent to the robot. The average absolute value was 0.031 and 0.027. So as a result, the robot based on these CMP slightly weaved in some cases. In the bottom figure, finally, the average absolute value based on the deep neural network at the 200th epoch was reduced to 0.008. So the robot based on the CMP was enabled to move in a straight line toward the destination. As the network training further proceeded, the straight line stability of the CMP approached the one of the DMP. In this regard, however, while the DMP was based on the deep neural network at the 30th epoch, the CMP was based on the deep neural network at the 200th epoch. This result indicates that the effectiveness of the discrete motion planner for autonomous navigation of mobile robots at the lowest possible training cost. In conclusion, we have proposed two end-to-end continuous and discrete motion planners based on deep neural networks for autonomous navigation of mobile robots. As a result, the robot was allowed to successfully move toward the destination while avoiding the obstacles. Through the navigation experiments, we showed the higher straight line stability of the discrete motion planner. Moreover, although the straight line stability of the continuous motion planner was improved, the effectiveness of the discrete motion planner for autonomous navigation of mobile robots at the lowest possible training cost was shown. Okay, that's it. Thank you for your kind attention.